All right, let's look at our titration curve. So there's a couple of points that we want to measure the pH at during our titration. All right, first is the initial pH. So before I've added in any of my titrant, I want to measure what the pH is. I then want to measure between the initial pH and the equivalence point. So that's when I've either neutralized all of my titrant. Right? I want to measure it at the equivalence point, and I want to measure it sometime after the equivalence point. And I end up with a titration curve, which is a graph of pH as a function of the volume of added titrant. So I've got this is a strong acid being titrated with a strong base. So my x-axis is volume of sodium hydroxide added. The missing title should be something along the lines of 0.1 molar, blah, 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 volume of whatever it is, titrate. So I need to know what the concentration is. So I'm missing the title, which will tell me the volume. Which will tell me the volume of the titrate. And I'm also missing down here at the bottom, what's the concentration of my titrant. Right, so those are two very important things that you want to include on your pH titration curves. Right? So the concentration down here and then the volume up here. Right, so let's look at some of these points. And we have the skills and the tools to be able to calculate the pH at any one of these little dots here. Any one of these points along here we can calculate, but for us to just be able to sketch the curve, I don't need to calculate all of them. I really just need to know where I'm starting, one in the middle, between the equivalence point and the start, the equivalence point, and then maybe a point afterwards, right? The calculations can get a little bit hairy right in here, right? Right here, this is just a strong base problem. Right, for our particular titration here. And here, right, this would just be a strong acid problem, and this is just going to be it's pH 7 because it's strong acid and a strong base. So let's look at this where I've got a strong acid and a strong base. We're going to start with 25 milliliters of 0.1 molar HCl, and we're going to add in 0.1 molar sodium hydroxide. So I'm going to start off with an initial we're going to add in 0.1 molar sodium hydroxide. I start off with an initial volume of 0 added sodium hydroxide, and my pH is going to be 1, right? Because it's just going to be 0.1 molar HCl. Take the minus base 10 log of that. I'm going to get a pH of 1. All right, so that's this point here. For the next point, we're going to add in 5 milliliters of our 0.1 molar sodium hydroxide. Right? So there we're going to add in 5 milliliters of our sodium hydroxide. We're going to convert the volume and the concentration to moles of sodium hydroxide. And then after we convert that to moles of sodium hydroxide, we do the stoichiometry. We figure out how many moles of H plus we have left over, divide by the new total volume, and we get the pH, 1.18. We can do this for 10 milliliters, 15 milliliters, 20 milliliters, right? I've got less and less H plus in more and more water, so my concentration of H plus is going up. My concentration of H plus is going down, so my pH is going to go up. Now, we calculate the pH at the equivalence point. That one is super easy for us to figure out the pH because it's a strong acid and a strong base. So at that equivalence point, we know that the pH is going to be equal to 7. How do I find that equivalence point? Well, first I've got to find the moles of titrant. The equivalence point means it's the moles of titrant equal moles of titrate. So then I need to determine the volume of titrant that has that many moles. Right, so here I've worked out the example of how to do it for our particular case here. And it comes out to 25 milliliters. Right? If this had been a more concentrated sodium hydroxide solution, right, twice as concentrated, well then my concentration of sodium hydroxide would be different. Right, which would mean that the volume of sodium hydroxide that I would need would be less. Once I've gone past that equivalence point, my pH is going to be controlled by the titrant. So here I've got excess titrant. Right, so I've got excess sodium hydroxide. So if I've got a point over here where I've added in 30 or 35 milliliters, right, I'm just going to be figuring out the OH minus ion concentration and then using that to find the pH. All right, so for the 35 milliliter version, 35 milliliter point here, it's going to, I'm going to calculate the moles of OH and the moles of HCl, because I got a volume and I got a concentration, I can get moles. I do the difference to find the moles of excess hydroxide. Take that moles of hydroxide divided by the total volume to give me the concentration, convert that to a POH, and then from there find the pH. All right, so what indicator would I use? This is an example of that titration, but using slightly different concentrations. Here I can use either methyl red, right, because it'll undergo a rapid pH change in the range of 4 to 12 over a very narrow range of added volume. So I could use either methyl red or I could use the phenolphthalein. Either one would work. To sum up, for the calculations for a strong acid, strong base, before or after the equivalence point, you're going to calculate the moles of acid and the moles of base. You're going to do a reaction stoichiometry table based on the reaction between the strong acid and the strong base to give you a salt and water and determine which one is in excess. If the acid's in excess, determine H3O plus from excess moles of acid and the total volume. Right? Which it should be before the equivalence point. If it's at the equivalence point, it's 7. Right? Moles of acid equal moles of base. If you've got base in excess, you're going to determine the moles of base and divide by the total volume and figure out the POH, and then from there find the pH. Right? What happens if you've got a weak acid and a strong base titration curve, right? Something like acetic acid and vinegar. Right? Well, for a weak acid and strong base titration curve, it's going to look a little bit different. So this represents, this little dashy line is the strong acid, strong base you had before. It looks very, very S-like. For the weak acid and strong base, it's a little bit different. Right? I can't use either indicator. Right? I can't use methyl red. I could still use phenolphthalein for this one, this particular titration. But I can't use this methyl red because I've got this long, slow, drawn-out part where once I've added in some of my strong base to my weak acid, I've got a conjugate weak base, I've got a conjugate weak acid, I've got both of them in solution, and so I've got a buffer. And does a buffer change very much in its pH? No, it doesn't. So you're adding in increasing amounts of sodium hydroxide to our weak base, but it's actually adding it into a buffer, and so it's going to act like a buffer. And the transition is long and slow between 4 and 6. So my methyl red, which changes between 4 and 6, is not a suitable indicator for this reaction. So I've got to get the right indicator. All right, phenolphthalein. Right, my indicator is going to be 8.8 at, or my reaction is going to be 8.8 at the equivalence point, is going to be an acceptable indicator, but not the methyl red, right? Because along here, I'm Henderson-Hasselbalching buffering it, right? When we do the calculations for these, right, I can pick any point along this buffer region and do Henderson-Hasselbalch. We're going to actually just pick one, right? Where the conjugate acid and the conjugate base are an equal concentration to each other, and that's halfway to the equivalence point. So halfway to the equivalence point, pH equals pKa, makes our lives a little bit easier. Right. But let's look. The pKa of this indicator is below. It's not going to work for us. All right, so let's say we're going to do pyridine, right? So before any weak base is added, the solution contains only the weak acid, and we're going to do HPR. And our initial pH is weakly acidic. As we add in the strong base consumes a stoichiometric quantity of the weak acid, where we got our weak acid plus a strong base giving me the conjugate weak base and water. It's going to leave us a mixture of the conjugate acid and the conjugate weak base in solution, and that's going to be a buffer, and the pH is given by the buffer calculation. Where the pH change is the least, that is when the buffer is the most effective, is when the concentration of the conjugate acid and the conjugate base are the same, right? And that's going to give me pH equals pK of the log of this over this, which will be the same amount, which will be the log of x over x should be 1, so pH will equal pKa. At the equivalence point, all of my conjugate weak acid has been converted by the sodium hydroxide to the conjugate base. So it's just got the weak base in solution. The pH is going to be up above 7, and it's going to be basic at the equivalence point. After the equivalence point, we're going to see a huge jump in pH. It's going to be dominated by the excess hydroxide that we add in. So the pH is going to be way bigger than 7. And we can do the same sort of plotting out the individual points on a titration curve, like we did with the strong acid, strong base titration. But now we're going to do a weak acid with a strong base. So we're going to start with 25 milliliters of 0.1 molar, looks like formic acid, and we're going to add 0.1 molar sodium hydroxide. So at the initial pH, what kind of problem do I have? Well, the initial pH means just when I've got 0 added. So here, at the initial pH, so in the beginning, it's just the weak acid in solution. I can find H plus using my shortcut. Right, of H plus is equal to Ka times C, assuming X is small and comes out as 2.37. I can add in a little bit. I've got a little bit of conjugate acid. I've got a little bit of conjugate base. So now I'm in this buffer region. Anywhere in this buffer region, I can use the Henderson-Hasselbalch equation, pH equals pKa plus log of AHA. There is this special halfway point, right? So if I know my equivalence volume, which I should have calculated early on, halfway to that equivalence volume, I will have neutralized 1/2 of my conjugate acid and converted 1/2 of that into conjugate base. So now my conjugate acid and conjugate base concentrations are equal to 1/2 of my initial conjugate acid weak acid concentration, so that when I plug it into the Henderson-Hasselbalch equation, it's a log of something over the same thing. That's the log of 1 at 0, so at halfway to the equivalence point, 12.5, halfway to my equivalence point, the pH is going to be equal to pKa. So that's an easy, fun point to find. I can then go anywhere beyond this, add a little bit more, add 13 milliliters, do Henderson-Hasselbalch again. It's just that it's a lot easier to figure it out here because I don't have to go through and do the math to figure out, well, how many moles of conjugate acid and how many moles of conjugate base do I have? A little faster. Once I am at the equivalence point, so 25 milliliters in this case, I just have the conjugate weak base in solution along with some spectator ions. I don't have any of my conjugate weak acid. I can use this shortcut where my hydroxide ion concentration is equal to Kb times the new concentration. So this is going to be moles of the hydroxide divided by the new total volume. Right? So this CV is always going to be less than your initial concentration of your weak acid by some amount. In this case, it's going to be half the concentration because I've got the same number of moles, 0.0025 moles, divided by 0.025 liters plus 0.025 liters. So I've doubled the volume, same number of moles, double the volume, half the concentration. So make sure that you correct for this volume here. When I do this, I end up, I also need to convert the Ka to a Kb. I'll end up with a slightly basic solution, which makes sense because I've got just base in there. I add in a little bit more of my hydroxide, and the pH is going to shoot way up because now I just have excess hydroxide in solution. I treat it just like I would for the strong acid, strong base titration where I've got excess hydroxide. So for example here I've got 15 milliliters of excess hydroxide and I would end up with a pH of 12. Right. Let's do a practice problem. So I've got hypochlorous acid. It's got a pKa of 7.54. I've got 45 milliliters and of a 0.24 molar hypochlorous acid solution. I titrate it with 0.25 molar KOH. What's the pH at the equivalence point? Pause, come back. Good. All right. Now the answer is 10.31. There are numbers I could eliminate right away, right? So I started off with a weak acid. I'm titrating it with a strong base. I know that at the equivalence point, I just have a conjugate base in solution, which means these two guys, which are acidic, I can eliminate. 7.41 is actually pretty close, so I might think about eliminating that. How would I do that? Well, I would need to take my Ka and I would need to change it into a Kb. And then I would use my shortcut that the hydroxide ion concentration is going to be the square root of KB times point times the new concentration. So